All right, I just started the recording for our April 16th meeting of political analysis. Today is the second to last substantive in-person meeting that we're going to have. We're going to cover some advanced regression techniques in class next week, including logistic regression and interactions. And then after that, your final papers are due, and we're going to spend our last in-person meeting doing exam review and going over anything that you might want to discuss for that. But here's the plan for today. We're going to review our materials on regression assumptions. And in particular, we're going to focus on testing hypotheses with regression. We talked about hypothesis testing in class last week, but we were doing something a little different than what we're doing with regression analysis. And then I'm going to spend a little extra time focusing on including categorical variables in regressions. We did this online a little bit this week, but it can be a little tricky interpreting them. And I have a feeling that for a lot of your papers, you're going to need to use this technique in the analysis part. So we'll focus on that. And after we review conceptually how that works and how to interpret those things, we'll end the class by doing some more Excel tutorials. So I posted some sample data from the American National Election Study up on Blackboard this morning under that Zoom materials and face-to-face meetings link. It should be down at the bottom. If you want to download that now, once we get into the tutorials, you'll be able to follow along with what I'm doing if you would like to. Okay, so I mentioned just a minute ago that over the last 2 or 3 weeks, we've been talking about hypothesis testing, both conceptually what it means, and we've been applying that to hypothesis tests that involve comparing means, either across groups or to some sort of value in the population that in reality we don't usually know. But we talked about a couple of tests. You'll recall a t-test allows us to compare two means to one another. And then if we want to compare means across more than two categories, we have to use an ANOVA, which is a separate test statistic, and a slightly different interpretation of what the hypothesis test tells us. But all this is to say that this type of hypothesis testing that we've been doing is something that we can think of as a bivariate regression or bivariate analysis. Bivariate just means two variables, right? An X and a Y usually. So in the ANOVA as well as the t-test that we've been practicing doing, we can think of whatever our grouping category is as one of our variables. So maybe, we looked at means for things like political interest and tested whether they differ for men and women, right? So in a survey, the respondent sex is one of the variables, political interest is the other, and this is a bivariate analysis. Same thing with ANOVA. If we have more than two categories that we're looking at means across, still, whatever is the categorical variable is one variable of interest, and whatever we're comparing the means on is the other one. So in terms of mathematical notation, right, we talked about the null hypothesis. If we were doing it something like a t-test, we would write something like this. The null hypothesis is that mean 1 is equal to mean 2 for the two different groups. Or that the difference between these means is 0. And then usually an alternative hypothesis is what we're interested in trying to validate. So the alternative hypothesis might look like this, right? The means are not equal to one another, that there's a difference between them that is significantly different from 0. Or maybe we might pose a directional hypothesis. For instance, the mean for women is greater than the mean for men. So, just keep that in mind, because when we get into talking about regression, even though we're going to be adding more than two variables, we're going to be doing multivariate analysis. The logic here is still similar. And what regression allows us to do is assess how multiple independent variables, so more than just one, simultaneously affect an outcome, a dependent variable. So once you start estimating regressions in Excel, you'll get this output with regression coefficients. For each independent variable that we're interested in, the null hypothesis essentially is that beta equals 0, meaning that the independent variable has no effect on the dependent variable, that it's 0. And then the alternative hypothesis, just like if we're comparing means, is that the beta or the coefficient is different from zero. That is to say, there is an effect. As x increases, y might also increase, or it might decrease. Right? So I want to review this just a little more. I've noticed over the last couple of weeks, we're still struggling a little bit with talking about hypothesis testing and figuring out, based on output in Excel or another statistical package, when we should reject the null hypothesis and accept the alternative. So someone remind us, what are we looking at in Excel to tell us whether or not we should reject the null hypothesis and conclude that there is some real world difference that is reflected in our data? What are we looking for? Excel's going to tell you two things. It's going to calculate what we call a test statistic, depending on what test you're doing, and then it's going to tell you a corresponding critical value that corresponds to a specific distribution, as well as whatever probability level you have stipulated at the outset. What do we do?
If the test statistic is greater than the critical value, we reject the null.
Correct. And if it's greater than or equal to, we're going to reject the null and conclude that there is some sort of relationship. So that is why we say big test statistics are good. If you get a really big value, say, like 50 or 100, 200, something like that, it's almost always going to be greater than or equal to whatever the critical value is, right? So when the test statistic is greater than or equal to the critical value, or another way of saying that is when the p-value, something Excel also reports for you, is less than alpha, which corresponds to the confidence level you've set out at the beginning of your analysis. These refer to the same things. That's when we reject the null. So I wanted to build on that a little bit by just discussing the logic behind that. Why is it that big test statistics correspond to p-values, and why are they good things, right, for making causal inferences? What you should remember is that critical values, the things that we're comparing the test statistic to, these correspond to standard deviations from the mean in a standard normal distribution, right? So this logic, as we've said over the past few weeks, applies to any sort of test we're doing, whether we're doing a z-test, t, f, chi-squared, whatever. They're all probability distributions that just have different shapes. And if we look at the standard normal z distribution, the critical value corresponds to what is on the other side of a standard deviation away from the mean, basically the area between that critical value all the way out into the tail. So the logic here is that as we move further and further away from zero, the portion in the tail is going to get smaller. That's what we want. We want to minimize that, right? So we can think of this standard normal distribution as having an area of 1 underneath it. And if we're trying to minimize the probability that we reject the null hypothesis when it's actually true, right? This is a type 2 error. This is what we're trying to minimize. And those critical values, here it's a z-score, but again, it could be a t and f chi-squared, any sort of test, any sort of distribution. We want to get as far out into the tail as we possibly can. We want to minimize that probability of making the type 2 error. So the logic here is that if we have a really big test statistic that's going to be really, really far away from the center of the distribution, way out in the tail, it's probably going to be way further out there than our critical value. So there's a much slimmer chance of incorrectly rejecting the null hypothesis if it's actually true. So all this is to say, we want really large test statistics. Okay, so the next thing we want to talk about is the difference between correlation and regression. These are both statistics that we can calculate in Excel that tell us something about an association between variables. You know, when you first start learning about these things, it can be a little confusing to figure out what regression tells us that correlation can't, because remember, both of these things tell us something about the strength and the direction of a relationship. So the main difference is that when we're doing correlational analysis, this is what you did in lab assignment 4, what we're doing is producing just one single statistic. It's relatively easy to calculate in Excel. We looked at multiple ways of doing it. So we might ask ourselves, well, why might we not want to just stop there, right? If we know that as X increases, Y also increases, and then it's a fairly strong association, what more could we possibly want to know? So the reason that we turn to regression is that it produces an entire equation. All correlational analysis does is tell us how things move together. It makes no assumptions about causality, right? So, you know, that we can calculate correlations for relationships that are completely spurious. Regression allows us to minimize the chances of making that type of error, right? And regression is actually a test of a cause and effect type of relationship. Rather than just looking at how two variables, X and Y, move together, regression will allow us to know precisely how a change in X affects our outcome, our Y. So it produces an entire equation with lots of different statistics that we need to look at, rather than a single statistic, as we would get with correlational analysis. And what this equation does, since it tells us how changes in X affect Y, is it allows us to make predictions. That's why regression is such a powerful tool. So I mentioned a minute ago, and as you learned about in the online materials this week, the basic regression equation is written usually like this. You might see some different notations that correspond to different disciplines, but usually this is how a political scientist will write a basic regression equation. So let's look at each one of the different components. If we say that y equals alpha plus beta times x plus E, the y component of this equation is just going to be the predicted value of our dependent variable, given whatever is on the right side of the equation. Then if we move over to the right side, on the other side of that equal sign, the first thing we encounter is denoted by alpha, which refers to the y-intercept. So if we set all of the values in the equation to 0, that's going to be what alpha is, right? So we need this in the equation for mathematical reasons. We need it to generate those predicted values, but in substantive terms, usually, not always the case, but usually it's meaningless. And the reason that it's meaningless is that if we're studying real world events, lots of things can't actually take on the value of 0, or it might not be within the range of the data that we're looking at. For instance, if age is a variable that we're including in our regression analysis, it doesn't really make any sense to say that a person who is 0 years old would do anything, right? It's meaningless. But nevertheless, we need it for the equation. And in your output in Excel, this can be labeled a couple of different ways depending on which package you're using. Sometimes it's labeled as the intercept, which is what Excel does. In programs like Stata, it'll be called the constant. Constant and intercept, they refer to the same thing, right? And then the thing we're really interested in the regression output and equation is the beta, or multiple betas if we're including multiple independent variables. Each independent variable will have its own regression coefficients. So this is another constant. It's not a variable, but what it does is it allows us to know how, when variables change, how does that affect the outcome variable, the dependent. And in mathematical terms, what these regression coefficients are, what you can think of them as, is the slope of a line, right? So this goes back to basic algebra, rise over run. If we move 1 unit on the x-axis, what's going to happen on the y-axis? Is it going to go up? Is it going to go down? How much is it going to change? And then in statistical terms, we refer to these slopes just as average effects. And then the next thing that's important, particularly if you're going to be generating predictions, is x. X is just whatever value the independent variable takes on. That's what you actually plug into the equation that changes. Everything else in there stays the same. And then finally, we have to write this as part of our equation, the error part on the end, but we don't actually know what it is, right? It's not something we're going to plug into the equation. We're just acknowledging that whatever regression equation we come up with is never going to perfectly explain all of the variation in our dependent variable. If we perfectly knew how to predict y, then we wouldn't need to be doing regression in the first place. And this is why it's important to pay attention to either the R squared or the adjusted R squared value in the statistical output. Remember, R squared is telling us how much of the variation in the dependent variable is explained by all of the stuff on the other side of the equation, all of our independent variables. And you're never going to see an R squared value that equals 1. It's always going to be less than 1. Ideally, we want it to be a large number. We want to explain a lot of the variation in the dependent variable, but it's never 100% perfect, right? Because we're dealing with probability here. So again, all that's to say we need to acknowledge that error exists, but we don't have anything to plug in there. It's something we note mathematically when we're writing this out. Okay, so let's look at an example. Again, we've got our basic regression equation, y equals a plus bx plus error. And we can think of two variables from survey data. This particular data comes from the Latin American Public Opinion Project. So we've got a variable that measures trust in the legislature on a 1 to 7 scale. 7 is more trust, 1 is no trust. We've got a question about perceptions of the economy. Higher values on that correspond to better evaluations. And then what I've got here is some output from Stata instead of Excel. I think it's important to show you output from multiple different statistical packages, even if they're not the ones you're using, because you want to be able to figure out what the values are, right? Usually they're all labeled the same way. They just might be in a different place in the output. But if I run correlational analysis in Stata, the same thing you can easily do in Excel, we get this correlation coefficient of positive 0.1608. So somebody just remind us, that's a correlation coefficient. How would you interpret that? If you had to do that on lab assignment 4, what would you say? Remember, strength and direction. That's the only things that correlation really tells us. What would you interpret that 0.16 as meaning?
It's a weak positive correlation.
So we would say that as trust in the legislature increases, so do positive perceptions of the economy, or vice versa, right? We're not making any assumptions about causality here. Regression, though, remember, it can tell us something different. So if we run a regression analysis and we're going to assume that perceptions of the economy cause trust in the legislature, theoretically, that's the more logical direction for this relationship to go, we would get some output in Stata that looks like this, right? So we've got a coefficient on our independent variable measuring perceptions of the economy. We go over to the right a little bit, we'll see a t-value, looks pretty big. We see a p-value, which essentially rounds to 0, so we can say it's really small. And then we'll get a confidence interval around that estimate. We see that it doesn't overlap with 0, so we can assume there's some effect here. And then in Stata, as opposed to Excel, rather than calling the y-intercept intercept, it's labeled as _CONS here, which just means constant, right? So what's this regression output tell us that the correlational analysis doesn't tell us? What can we infer from this output? And we really want to practice this because this is essentially what you're going to be doing in your final paper. Let's start with the coefficient on our independent variable, perceptions of the economy. How would you interpret that? Just in intuitive terms. I'm still here, still waiting. 0.318. How would we interpret that?
Would it be for every unit increase of trust in the legislature, you have a unit increase of 0.318 of the economy?
So I'll flip it around, but you're essentially right. So we're trying to understand how perceptions of the economy affect trust in the legislature. So we have to change perceptions of the economy first in our interpretation. So we would say that for a 1 unit increase in perceptions of the economy, 1 unit corresponds in this case to how that variable is measured. In this particular data, I can't remember, but I believe that this is a 3-point scale. So we would, if we go from 1 to 2 or from 2 to 3, both of those changes would be associated with a 0.318 increase, because we have a positive sign here, in trust in the legislature. So that 0.318 increase is in relation to the 7-point scale that trust in the legislature is measured on. So we say units because depending on how the variable is measured, those units could be different, right? So, this is why it's sometimes hard to directly compare the magnitude of one regression coefficient to another, because each of the independent variables is usually measured on a different scale, right? So bigger values don't always mean a stronger relationship, right? So, that's what we would call our average effect. And then remember, the next thing that regression is useful for is generating predictions. So what we would do is we would take all of the output from this analysis and we would start plugging things into that basic regression equation. So if someone, okay, so maybe the economy question was measured on a 1 to 5 scale. This varies from survey to survey. But if we wanted to know on average a person who answered 4 on the economy question, so pretty good perceptions, but not the best. On average, what would we expect their trust in the legislature to be? So trust is our dependent variable, our y hat, our outcome we're trying to predict. And then we need to go and grab different values to plug in from that table. So we're going to start with alpha, which is our y-intercept. That's identified in the table here as 2.65. So that's our starting point for the line on the y-intercept. And then since we have a positive coefficient on the economy variable, we're going to say plus 0.32, right? That's the regression coefficient, times 4, which is our value of the independent variable. And then we're going to add that up. Right? Okay, so that is just at its most basic how we can use bivariate or multivariate regression to generate predictions. If you had more than one independent variable, you would just keep doing that, beta times the value for each variable in the equation. And like I said, linear regression is a really powerful tool because it allows us to make these sorts of predictions and estimate average effects, test causal relationships. But it's important to also acknowledge that it's not always appropriate to use this in the real world, even though I'm going to tell you, all of you, to just use ordinary least squares linear regression in your papers for this semester. And the reason for that is that this is a really powerful and robust tool so long as we're meeting certain assumptions about our data. If all of the regression assumptions are met, this produces what we call the best linear unbiased estimate, which is usually abbreviated as BLUE. So if our regression meets these assumptions, if it's really the best linear unbiased estimate, that means that the estimates that we produce are going to approximate the true population parameters, right? This is what we want. We're trying to generalize and make inferences to whatever our population of interest is. Unbiased also means that both the coefficient, so the value of the regression coefficient, our beta, as well as the standard error, which is the measure of variability, which has implications for uncertainty. Unbiased means that both of these things are correct as well. And for hypothesis testing, we can make a trade-off, right? Generally, what we're just interested in is the direction of a relationship and whether or not it's significant. So it's okay in the grand scheme of things for hypothesis testing if our beta, our regression coefficient, isn't 100% accurate, so long as the sign is accurate. Where we get into trouble, though, is if we have biased standard error estimates. And the reason for this is we are never going to know if they're correct or not, if we're not meeting these assumptions. So it's the standard error that determines whether we accept or reject the null hypothesis. So if the estimate is biased, we might make a type 2 error, right? We might conclude that there's no relationship when there actually is, or we might conclude that there is a relationship when there actually isn't. So it's really important to, at least double check your data to make sure you're meeting most of these assumptions. And a lot of the assumptions in linear regression that you read about in your textbook for this week, they're assumptions related to the error term or the residual, right? That Greek letter E at the end of our mathematical equation. So when we say error term or residual, what we're talking about is deviations from our regression line. So these can be above the line, they can be below it. Some of them can be small deviations, some of them can be large. Remember, we're just gonna square all of these and average them when we're calculating regression coefficients and standard deviations. So that's what we just said. They can be positive or negative depending on whether they're above or below the regression line. And if we make a scatter plot with values of the independent variable on the x-axis and our residuals or the error values on the y-axis, the big regression assumption is that this distribution should be completely random. There shouldn't be a relationship between independent variable values and error values. If so, we're getting ourselves into some trouble, right? We're not meeting those linear and unbiased assumptions. Right, so you'll remember again, the error terms, these are that unexplained variation in the dependent variable. If that unexplained variance is correlated with the independent variable, what it's gonna do is create a biased estimate. So we just know that there are deviations, we don't necessarily know what's causing them. It's unexplained. So in addition to that, we also need to assume that our errors have constant variance, so random distribution across all of the values of y hat. So if we use that regression equation to generate a bunch of predictions, the deviation of each independent variable from the regression line shouldn't have any relationship to the values that we're predicting. And this is usually the most common violation when doing linear regression. And there's some statistical fixes for it that you can't do in Excel, but you'll read about a lot. So this is what a non-constant variance would look like, right? So we can, we would expect that all of these would be kind of randomly clustered above and below the 0 line. We could draw a horizontal line straight through it. But instead, we see clustering as our linear predictions increase. This is what we would call heteroskedasticity. It's a big word, it's problematic. There's statistical fixes for it, but if you don't account for this, it can create biased estimates. And one of the most common ones that you'll read about, particularly if you're carefully reading, particularly the notes underneath regression tables that tell you what everything means, is to use a correction called robust standard errors. So this just basically makes your standard errors more conservative, right? So bigger confidence intervals, they reduce the chances of estimates affecting your hypothesis test. You can't do this in Excel, but like I said, you'll encounter it a lot in regression, in research articles that use linear regression. And that's what that means. It's a correction for this sort of assumption violation. Okay, so the final thing we want to talk about before we look at some tutorials is why not just stop at bivariate regression? We said that bivariate regression is an improvement over correlation because it tells us something. Usually we're just interested in the relationship between our independent and a dependent variable. Why include all of this extra stuff in our equation? So, just to start off talking about this, you'll remember that when we include a continuous control variable in the model, usually what you'll see is that the goodness of fit statistic is going to improve and that the coefficient on the independent variable of interest should change a little bit. So the reason for this is that control variables are helping us explain some of that unexplained variance that we observe when we're just estimating the single slope of a single line, right? So they explain extra variation in both the independent and the dependent variable. The reason we do this is because we're attempting to control for additional sources of spuriousness, something, again, we can't do if we're just doing a correlation. So let's look at an example. Again, I'm going to show you some output, I think from Stata, but I want to show everyone how when we go from estimating a bivariate to a multivariate regression, some of these things change. So I'm going to use some data from the American National Election Study that includes measures about political ideology. It's a 1 to 7 scale where higher values indicate more conservative, lower values are more liberal. As well as that dependent variable we looked at last week, the 0 to 100 feelings thermometer of the Black Lives Matter movement as measured in 2016. So if we just start off with the main relationship we're interested in between ideology and that feelings thermometer measure, we can estimate a bivariate regression. Again, let's practice. What does this tell us? What's the average effect of political ideology on this particular feelings thermometer? The coefficient is a negative 10.78. What's that mean? If higher values of ideology indicate more conservative and we have a negative regression coefficient, what's kind of the big picture and inference we can draw? Or put a different way, who has warmer feelings toward the Black Lives Matter movement, according to this data, liberals or conservatives? Yes. And the converse of that, since we have a negative sign, is that conservatives have more negative feelings, right? So,
Yeah, so
as
it goes up.
yeah, so exactly. Exactly. So yeah, just think of this stuff as, again, slopes of a line. So the more detailed intuitive interpretation we would say is that for every 1 unit increase in our ideology measure on that 1 to 7 scale, so as it becomes more conservative, on average we would expect to see about almost an 11-point drop in this feelings thermometer measure, which is, I remind everyone, measured on a 0 to 100 scale. So that's pretty significant, right? About a 10% drop for each 1 unit increase in the ideology measure. So, you're hardly ever, if ever, going to just see a bivariate relationship reported. It's always going to be multivariate regression. So the thing I wanted to show you here is that the story doesn't really change once we start including additional control variables. Just some of the statistics change a little bit. So since we included this other feelings thermometer measure about the police, as well as a measure of political knowledge based on people's news consumption, that accounts for a little more of the unexplained variation in the dependent variable. You'll see our adjusted R squared goes from 0.29 to about a 0.31. So, we're explaining a little more by including control variables. We're ruling out the possibility that any of these extra variables are sources of spuriousness. And then you'll see, the relationship is still negative, but that average effect, since we've got other things explaining the dependent variable, it decreases in magnitude just a little bit, right? It goes from negative 10.78 to negative 10.01. So we would say that negative 10.01 it's a more precise estimate of an average effect. Okay, so those are continuous variables. The other type of control variable that we might include in our model is a categorical variable. And I say here, we have to be really careful in both how we deal with these in Excel as well as how we interpret them. So categorical variables, when you include them in regression, you have to take some extra steps. If you have a race variable, for instance, where each number corresponds to a different self-reported race, you can include that in your regression analysis. All Excel is going to do is look and see that you have values from like 1 to 5 or 1 to 8, and it's going to treat that like a continuous variable. It's going to give you a regression coefficient that has absolutely no meaning whatsoever. but it's a really easy mistake to make. So just pay attention here and be really careful when you're doing your own regressions. So what we need to do for the analysis, and we'll look at this here in a minute, is we have to start off by creating a series of mutually exclusive, what we would call dummy variables. Dummy variables are just 0, 1. You either are that category or you're not. So, if we have 3 categories, we're going to create 3 separate variables. Maybe we would say black, white, and other. So if black is 1, white is 2, other is 3, then the first variable is going to be called black. It's going to get a 1 if they answered 1, a 0 if they answered 2 or 3, right? Then for the white category, if a person has a value of 2, they'll get a 1 for white, a 0 if they have 1 or 3, so on and so forth. So you have to do that. And then you have to exclude one of these categories from your regression. You can't throw them all in there. If you do, the statistical package is just going to kick one of them out. But it's better for you as the researcher to have control over whatever the reference category is that you're comparing to. And then the way we interpret the coefficients on these isn't as the slope of a line. What you interpret it as is different starting points for the line on the y-axis, right? So we're just moving the line up or down. These coefficients aren't telling us about slopes anymore. So again, we'll look at an example. Same bivariate regression as before, but we're going to include a control for self-reported race from the American National Election Study. And going back to our previous example, this looks familiar. That's the bivariate regression output we looked at. And then we can see how this equation changes a little bit once we include the additional control. The main thing we see here is that our goodness of fit improves significantly, right? It improves by around 5%. So again, in this, the category that I've told the program to exclude is white. So we interpret each of these coefficients in relation to the category of white. Already said that. We improve our goodness of fit statistic by doing this. And then what we would say is that for each of these, with the exception of the coefficient on Native American or Alaskan, that's not significantly different from whites. All of the others have significant coefficients and they're all positive. So we would say that for each of these survey respondents, the starting point on the y-axis on that feelings thermometer is going to be higher than for white respondents. So, that's how you interpret it. We can assume that the relationship between ideology and the feelings thermometer, like I said, we'll assume that it's the same for each of these. Just the line is going to start, above or below some point on the y-intercept. And if we graphed it, this is what that would look like, right? So we see the same average effect for whites, blacks, and Hispanics graphed here. As people become more conservative, they have less warm feelings toward the Black Lives Matter movement. Slope of the line is the same for each of these categories. It's just that the starting point is lowest for white respondents, whereas it's highest for Black respondents, and then Hispanic respondents are in between. Make sense? Right? And again, the choice to model it this way is based on your theoretical assumptions. We would probably also assume that the relationship between ideology and our dependent variable is going to have a different slope for each of these groups. But to test that, you have to use an interaction, which is what we're going to look at next week. Okay, so I have talked a lot. We've got about 10 minutes left. What I'm just going to do, we're going to skip the ANOVA tutorial since we already did one of those last week. You can go back and review the recording if you want to see how to do that again. I'm just going to walk everyone through the steps of conducting a regression with categorical variables in Excel. All right, so I'm going to switch over, make sure I'm showing my Excel. Like I said, this data is posted on Blackboard if you want to go back and work through it yourself. So here's the raw data, right? I've got a bunch of different measures from the American National Election Study. The first variable here is measuring political trust. I've got the corresponding codes over on the right-hand side of the screen. We've got a measure of political interest, a measure called female, which measures the respondents' self-reported sex. So we've got a variable for race, which we're going to be interested in. that is coded, as I say here, 1 equals white, 2 black, 3 Asian, 4 Native American, 5 Hispanic. Our dependent variable is the feelings thermometer. We've got a measure of ideology, and then some things we might include as control variables, namely news consumption and a separate feelings thermometer measure about the police. So here's what we're gonna do the regression on, these 3 variables right here. What's currently in column B is gonna be our dependent variable. So as you'll remember from doing the lab, we're gonna wanna move that over to the far left side of the screen when we start manipulating these things. We've got our measure of ideology, which we can just go ahead and include in the analysis, right? It's a continuous variable. We can treat it as such. But we have to do something with this variable called race. We can't just include that as a dependent variable. We have to split it up and create 5 mutually exclusive categories. Right? So there we go. So that's kind of what I've done here as a starting point. I've created a variable called white, black, Asian, Native, and Hispanic. So everyone who answered 1 in the survey, which corresponds to white, you'll see they have a 1 here. Everyone else is going to have a 0. If we go down, everyone who answered Hispanic, they're going to have a 0 for white, for black, for Asian, for Native American, and then they're going to have a 1 for Hispanic, right? So that's what we mean when we say including creating mutually exclusive dummy variables. A number that you create is going to correspond to however many categories or response outcomes there are on that categorical variable. All right, and then after we've done that, we can go ahead and ignore the original variable. We don't want to include that in the regression. So when you go and paste all of this stuff into a new screen, you might just want to delete this altogether so you don't worry about making a mistake. All right, so that's done. And then here we've got in the very first column, we've got our dependent variable. We'll highlight that so we make sure to put that in the right place in the data analysis thing. And then we can go ahead and do the regression now. So just like you practiced in lab 5, we're going to open up our data analysis toolkit. And we're going to select regression. Right. And we're going to assume that we've cleaned up this data, right? We've gotten rid of any row that has any missing observation on any of the variables. We're going to say y is whatever our dependent variable is. So that's here in column A. And you need to say, A1 through A, whatever the last row in the set of observations is. Right, and then for X, we're going to grab everything from, what I might do is actually rearrange this. So we're going to exclude whites as our reference category that we interpret everything in relation to. So we can also just go ahead and delete that category here so we don't mess anything up, right? We go back to the regression after we've selected our Y range, which is the dependent variable. Grab all of the independent variables now. So columns B through F, leaving white out. Tell it we have labels, output range, all of that stuff you already practiced doing in the lab assignment and that we looked at in here on Wednesday. And you will get a regression output that looks like this. Again, this should look familiar to everyone. And what I've done here is I've pasted in output from Stata, which is a different statistical analysis package. Just so you can compare across these 2 outputs. You'll see the values for everything estimated are the same. They're just in slightly different places on the screen. But once we've done that, right, we've got our overall intercept, which we can actually, since we excluded white from the equation, that's what it would have estimated for whites if we'd included it, right? So each of these, this is our average effect for ideology, and then each of these coefficients on black or white tell us something about the starting point above or below whichever category we excluded. All right, so all that is to say, we will interpret ideology as the slope of a line. We will interpret each of these coefficients here as different starting points for a line that has the same exact slope. All right, so that is everything that I wanted to go through today. Let me just switch over to PowerPoint again, because I do have an in slide with some reminders on it for everyone. As I mentioned at the beginning today, next week is going to be our final substantive unit of the class. It'll be really important to attend because we're talking about logistic regression, which is something you're going to read a lot about in your political science classes, though not necessarily perform in here. And then we're going to talk about some of those advanced regression techniques, such as interactions, which probably the majority of you will want to have a hypothesis about and test for in your final paper. And the interpretation can be a little tricky sometimes, so we want to just practice that again. Okay, and then final note I've got here, I haven't heard from anyone about getting access to survey data. And for anyone that's planning on using the American National Election Study, which is what I've steered a lot of you toward, you cannot download that data on your own unless you have Stata installed on your computer. You will need me to help you getting it. I can do that very quickly because I have the data. And give you an Excel sheet that just has the variables you're interested in, but you cannot wait until the last minute to ask me for this stuff because it's going to take time for me to help you out on your own project. So start looking through the questionnaires in the code books now, identify questions from any survey that you can't download the data for on your own, set up a meeting with me, and I will get you said data. All right, I hope everybody has a great weekend. Next week, you've got your final homework assignment due, and then after that, we'll be done with the class. We'll do exam review, and your final papers are due 2 weeks from today. So get working on those now. All right, I'll see everybody next week.